In this video, we're going to get into the big O notation and its relatives big omega and big theta. This can be a difficult topic, so I'm going to slowly build up to it and motivate why big O is defined the way it is. In the last lecture, we carefully counted how many comparison operations the double for loop algorithm for contains duplicate made in the case where the input had no duplicate. This gave us a fun problem, to sum the numbers from 1 to n minus 1, and we figured out that this sum is n minus 1 times n divided by 2. So we exactly figured out the number of comparisons the algorithm made, but probably we would like to answer different questions. For example, for how large an array will this algorithm still be feasible to run? Can we do it on an array with 100,000 elements? Or an array with 1,000,000 elements? To answer these questions, it's not clear if spending the time to exactly count the number of comparisons is worthwhile, because there are many other unknown quantities. How long does a comparison take? Does this vary from processor to processor? And how does it depend on the amount of RAM we have? Analysis of algorithms tries to make a general statement about an algorithm that does not depend on small details of the algorithm's implementation or the hardware on which it is run. Since there are unknowns present here anyway, usually in analysis of algorithms we allow for some slack in counting how many operations an algorithm makes. We shoot more for a back-of-the-envelope calculation that can roughly tell us if it is feasible to use a particular algorithm on an input of a certain size or not. The language that we use to classify the complexity of algorithms is called big O notation. This looks at how the running time or memory usage of the algorithm grows as a function of the input size. The first property of big O notation is that it ignores constant multiplicative factors. For example, n squared divided by 2 and n squared just differ by a constant multiplicative factor, namely a factor of a half. So since different implementations of an algorithm, or running an algorithm on different hardware, can easily result in a constant factor difference in running time, we zoom out our vision to see things that just differ by a constant factor as the same. And this lets us classify algorithms into broader categories. There's going to be a huge difference between an algorithm taking n steps versus one taking n squared steps as n grows large, no matter what kind of computer you're using. And this is the kind of distinction that we wish to capture. A side benefit of ignoring constant factors is that it makes our job analyzing algorithms easier. It's quite easy to see that this algorithm makes at most n squared comparisons. It's also easy to see that it makes at least, say, n squared divided by 4 many comparisons when the input has no duplicates. Since for every I from n over 2 to n minus 1, we have to make at least n over 2 comparisons. Thus, it's easy for us to classify this algorithm as making roughly n squared comparisons without doing any involved sums. Though I would still argue that doing the sum of the numbers from 1 to n minus 1 was pretty worthwhile and rewarding. So all this is not to say that constant factors are not important. Making your algorithm twice as fast in practice can be the difference between being able to solve your problem or not. It's just to say that the kind of analysis that we typically do in analysis of algorithms is too crude to make these kinds of specific predictions. If you really care about that level of optimization, you're better off doing benchmarking rather than counting steps in pseudocode. Okay, so that's the first important property of big O notation. We ignore constant multiplicative factors. Let's move on to the second key property of big O notation. Big O notation only cares about the growth of the running time as the input size becomes large. So let's look again at this picture we have for two algorithms for the contains duplicate problem. The yellow line is our double for loop algorithm, and the blue line is an algorithm based on hash tables. The x-axis is the input size. So in this picture, we're looking at small input sizes up to roughly vectors of size 1,000. You see that on small inputs up to size around 400, the double for loop algorithm is actually faster than the algorithm using hash tables. But for larger inputs, there's no contest. The double for loop algorithm is vastly slower. Big O notation does not care about what happens on small input sizes. It only talks about what we saw in this second picture, the growth of a function as the input size becomes large, actually as it goes to infinity. In terms of big O notation, we simplify things by saying that the blue line is smaller than the yellow line, even though the yellow line was less on inputs up to size 400. Okay, so that's some preparation for these two key properties of big O notation. We don't care about constant multiplicative factors, and we only care about the growth of a function as the input size becomes large. Let's move on to the actual definition. So we're going to talk about functions that map natural numbers to non-negative real numbers. You should think about the input to this function as being a problem size. So just think about it as the number of elements in a vector that you want to process. And think about the output as being a complexity measure. So something like the amount of time or the amount of memory that an algorithm uses. We restrict the output to be non-negative because that's when a complexity measure makes sense. And we also let it be a real number so that we can talk about functions like n squared divided by 2 that don't always take on integral values. So even though your complexity measure, something like time or memory, usually it's going to be expressed as a natural number, we allow it to be a real number just to make our life simpler. So finally, we come to the definition of big O notation. Let f and g be two functions that map the natural numbers to non-negative real numbers. We say that f of n is order g of n if and only if there are positive constants c and n naught, such that f of n is at most c times g of n for all n greater than or equal to n naught. So you see how this definition makes use of the two key properties that we talked about. This positive constant c is the slack of a multiplicative constant. And we only care about the behavior as n goes to infinity. So that is for n larger than this other number n naught. So it doesn't matter if on any finite interval f and g can do whatever they want. We only care about what happens in the limit as n goes to infinity. So let's look at some examples to get a handle on this definition. So the first example, we can see that 2 times n is order n. So if we let c be 2 in the definition, then we have that 2 times n is at most 2 times n for all n. So in this case, we can plug into the definition c is 2 and n naught is 0. So we can also see that 5n is order n squared. So of course 5n is always at most 5 times n squared. So in the definition we can take c to be 5 and n naught to be 0 again. But that's not the only way to see that 5n is order n squared. we can also see that for all n larger than, say, 6, n squared is just larger than 5 times n. So we could take c to be 1 and n naught equal to 6 in the definition of big O notation. So you can see that in the plot of the graph here, where I've drawn x squared and 5 times x. Let's look at a non-example. N cubed is not order of n squared. This is because n cubed is always eventually going to be larger than a constant times n squared for any constant c. Namely, once n becomes larger than the constant c, then n cubed is going to be larger than c times n squared. Here's a convenient, sufficient condition to check if f is big O of g. If the limit of the ratio of f and g as n goes to infinity exists and is at most a constant, then f is big O of g. Now you can't always use this test, as this limit might not even exist, but for the functions that we encounter in this course, they're always going to be nice functions, and this test should generally work. So this is a very convenient way to check if, when you're given two functions f and g in a quiz or something, you can try out this test to see if f is big O of g. For example, we can use this test to show that if a is less than b, then n to the power a is big O of n to the power b. So let's just look at the ratio of n to the a divided by n to the b. So that's 1 over n to the b minus a. And if b is bigger than a, then n to the power b minus a is going to go to infinity as n goes to infinity. So that means that 1 divided by n to the b minus a is going to go to 0 as n goes to infinity. Okay, and 0 is less than a constant, so this passes our test. And n to the a is order n to the b. Big O by itself is not enough to talk about the complexity of algorithms. It's just an upper bound, and there's no implication that it's the best possible upper bound. It's perfectly legitimate to say that the running time of the double for loop algorithm for a contains duplicate is order of n cubed. This is a true statement. N squared is order of n cubed. To really be able to compare algorithms, we also need some way to lower bound their running time. Donald Knuth introduced a notation to the analysis of algorithms to talk about lower bounds. And he did this in response to a misuse of the big O notation, where people actually use it to imply a lower bound. So let me read you this passage. This is a passage from a paper of Donald Knuth called Big Omicron and Big Omega and Big Theta, which actually introduced the notations of big omega and big theta into the analysis of algorithms. So he says, unfortunately, people have occasionally been using the big O notation for lower bounds. For example, when they reject a particular sorting method because its running time is order of n squared. I have seen instances of this in print quite often, and finally it has prompted me to sit down and write a letter to the editor about the situation. So do you see what the problem with the line in quotes? Order of n squared is just an upper bound. It doesn't mean that on some instances the algorithm is actually going to take time n squared. So this is no reason to reject a sorting method. Unfortunately, this exact misuse of big O is still very prevalent today. The notation introduced by Knuth in the paper I just quoted is big omega. Big omega can be used to lower bound the running time of algorithms. We say that f is omega of g if and only if there are constants c and n naught, such that f of n is greater than or equal to c times g of n for all n greater than or equal to n naught. So this definition is like a lower bound version complementing the upper bound version of big O. And in fact, you can express this definition in terms of big O. Namely, f of n is big omega of g of n if and only if g of n is big O of f of n. We saw that when an input does not contain a duplicate, the double for loop algorithm makes n-1 times n divided by 2 many comparisons. So on some inputs, the algorithm may make a lot fewer comparisons. For example, if the first two numbers in the array are the same, we would find that duplicate right away. But there exists inputs for which we have to make n times n-1 divided by 2 many comparisons. Because of that, we say that in the worst case, the case that maximizes the complexity, the input that maximizes the complexity, we have to make n times n-1 divided by 2 comparisons. Now we can see that n times n-1 divided by 2 is at least n squared over 4 for n at least 2. So we can say that the number of comparisons is omega of n squared. So we can say the worst case number of comparisons of the double for loop algorithm is omega n squared. We also know that no matter what the input of n elements we have, the double for loop algorithm always makes, at most, n squared comparisons. So it makes order n squared comparisons. That holds even for the worst case input, the input maximizing the number of comparisons. So we can also say that the worst case running time of the double for loop algorithm is order of n squared. So now we know that the worst case running time is both order of n squared and omega of n squared. And we have another notation for this important case, which is called big theta. For two functions, f and g, if there are positive constants c1 and c2, and an n naught, such that f of n is both at least as large as c1 times g of n, and at most c2 times g of n, for all n greater than or equal to n naught, then we say that f of n is big theta of g of n. In other words, for large enough n, f of n and g of n are within constant multiplicative factors of each other. So another way that you can put this is that f of n is big theta of g of n, if and only if f of n is both order g of n and omega g of n. In analysis of algorithms, generally the ultimate goal is to characterize the complexity of an algorithm in terms of big theta. That is, we want to both give an upper bound on the running time and a lower bound on the running time that are within constant multiplicative factors of each other. So we have characterized the running time of the double for loop algorithm in this sense. We can say that the worst case running time of the double for loop algorithm for a contains duplicate is theta of n squared. I will give you many examples of how to correctly use the terms big O, big omega, and big theta in this course. Unfortunately, when you read other sources, you should be skeptical because many people use these terms incorrectly. The exact same observation of Knuth from 1976, when he first wrote his paper introducing the big omega notation, is still very prevalent today. People use big O when they actually mean big omega or big theta. So this has always frustrated me, and I find that this misuse is actually acknowledged and ensconced in the industry use of these terms. So I was looking at this Cracking the Coding interview book the other day, and this is explicitly stated there. It said there that in industry, people seem to have merged big O and big theta together. Industry's meaning of big O is closer to what academics mean by big theta, in that it would be seen as incorrect to describe printing an array as taking time order of n squared. In this course, I hope to teach you how to use these terms properly. So every time you use big O or big omega or big theta, just take a moment to reflect and think about what you really mean. Do you really mean big O, or do you want to use big theta or big omega? I hope that you'll be a force for good and use these terms properly.